Start from the first page. Start from the first page. Start from the first page. Hi, can everyone hear me? Start from the first page. Hi, can everyone hear me? Hi, can everyone hear me? Hi, can everyone hear me? If you can hear me, everyone hear me? Say so in the chat. If you can hear me, everyone hear me? Say so in the chat. If you can hear me, everyone hear me? Say so in the chat. If you can hear me, everyone hear me? Awesome. Say so in the chat. If you can hear me, everyone hear me? So I'm hoping the two people who replied aren't just the ISAs. So I'm hoping the two people who replied aren't just the ISAs. So I'm hoping the two people who replied aren't just the So I'm hoping the two people who replied aren't just the So I'm hoping the two people who replied aren't just the So I'm hoping the two people who replied aren't just the Like, unfortunately, it's just however my internet is. However my internet is that at least like understandable? 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 Okay, well, for anyone else here, we're just going to wait a couple more minutes before the official start time. If you have any questions, please feel free to ask them in the chat now. Okay, that's terrifying. We'll just wait a couple more minutes before the official start time. How's everyone's quarantine going, I guess?
Deck, even though it's all legendaries.
Before this all starts. 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 Pass around quarantine bin. 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 Before this all starts. Just give people one more minute to maybe tune in, and then we'll get started. One more minute. Oh, I guess now this is 3:30. Okay. So, hi guys. My name's G. Welcome to the change anything. I'm just using my laptop. No, I didn't change anything. I'm just using my laptop. How about now? I didn't change anything. I'm just using my laptop. How about now? I didn't change anything. I'm just using my laptop. How about now? I didn't change anything. I'm just using my laptop. How about now? I didn't change anything. I'm just using my laptop. Okay. So apparently I'm still echoing. So I'm not sure if there's so much I can do about that. Does this sound really bad, or is it kind of bearable for now? I'm not sure really bad, or is it kind of bearable for now? I'm not sure really bad, or is it kind of bearable for now? I'm not sure really bad, or is it kind of bearable for now? I'm not sure really bad, or is it kind of bearable? Hey, can I use your headphones? I need the headphones. Hey, can I use your headphones? I need the headphones. Apparently my mic is no good. Thanks. I need the headphones. Apparently my mic is no good. Thanks. I need the headphones. Apparently my mic is no good. Thanks. Alright, how's that? Alright, how's that? Alright, how's that? Any better? Alright, how's that? Any better? Alright, how's that? Okay. So, any better? Unfortunately, I don't think there's much I can do about it. Any better?
I'll just try and continue and if about it, very bad quality. I'll just try and continue and if about it, very bad quality. I'll just try and continue and if about it, very bad quality.
Okay, so as I was saying, we have no name function where we can just name it anything we want. In this case, we chose F, and we said so by saying define. So if I wanted to call this function for a later purpose, to invoke it, to be able to do some addition, all I have to do is refer to it by its name, F. I can give it the parameters I want, and it can then very easily going from left to right and evaluate to make sure every single one of our parameters are in its simplest form. So going from left to right, the first thing we have to do is sum up 4 scores, we get 10, and then finally we do 10 multiplied by 5 to get our final answer of 50. So any questions about stepping through a simple lambda expression? Or really lambdas at all? Okay, if not, then I'm going to move on to abstract list functions, which is the other thing you guys have learned this week. So a couple of very common abstract list functions that you guys should know include filter, map, foldr, foldl as well, which is missing from the list up here. We'll add that in, and filter. So abstract list functions is another one of those daunting things to imagine, because once again, it's not anything we've really seen before. A lot of times we kind of know what they do if we just give it something. For example, filter, it magically produces the result that we want, but we don't actually know about its inner workings. So when it comes time to even change up the functions a little, it becomes very confusing. So what I'm actually going to do is show you guys kind of step-by-step examples of exactly how each and every single one of these abstract list functions works, and hopefully that'll give you a better idea of how to then kind of deconstruct, write them on your own, or use them within your functions. So to start off, let's look at filter. So essentially what filter does is it takes in is this the right slide? Oh well, this is the slides I have then. Filter. So essentially what filter does is it intakes a predicate and a list of values, and then one at a time applies the predicate to each of the values in the list. And each time to each of the values in the list. I am watching my stream, but I have my mic turned off. How about now? Is this better? Is echoing gone? Okay, awesome. We fixed the echoing issue. Great. So starting with filter, we know that, so we take our predicate and then we apply it one at a time to each of our elements inside. And then from here, we say if it produces true, then we want to keep it and put it within our list that's being produced. If it produces false, then we want to ignore it completely. So that's the inner workings of filter. And then from the next one we can look at is map. So map works in a very similar way, where you give it a function and one at a time it applies it to every single element inside your list. So starting, if I, for example, use add 1, then I can apply to the first in my list, which is 1. Then I add that result to my new produced list, which is 2. I apply add 1 to 2 to get 3, add 1 to 3 to get 4, add 1 to 4 to get 5, and add 1 to 5 to get 6. And in the end, I'm produced a list of the exact same length that I started with every single element modified by my given function. So this is the inner workings of map. So a really good difference to note between filter and map, especially if you're deciding when to use which one, is that map will always give you a list that is the exact same length as the one it started off with, whereas in case for filter, it may produce to you a smaller list. So if you ever want to decide which one of the two to use, this would be a great way to distinguish between that. Oh, so this was the animation I was looking for. I had apparently just put it a little far back. Don't worry, we'll use it for the upcoming ones instead. Okay, so the next function we're going to look at is build list. And essentially, this can be an example that we look at. Build list intakes a nat and then intakes a function which can intake a nat and then produce to you something else. So how build list really works is it's kind of a mixture of itself and map. So given the natural number, for example, 3, build list will first build you a list starting from index 0 and then up to 1, 2, so of a length 3. And then what it does is it takes the function that you gave it and then applies it to each of the elements in the list that it had just built. So it'll always start at index 0, building a list of the length you want, and then it takes the function you want and it applies it to each element. So in this case, if I add 1 to each of my elements, the final list I will produce to my end users is list 1, 2, 3. And then second last, but definitely not least, is foldr. And this is starting to become one of the harder functions that people usually struggle with, which are usually foldr and foldl. So what we like to say is foldr is really just an abstraction of simple recursion. So anything you can do with simple recursion, you can do using foldr. And if you didn't think templates were important back then, you're going to actually see how templates can really help you understand how to use foldr now. So once again, let's start with an example. So starting with this example of foldr, where the function I pass it is cons, the value I pass it is empty, and the list I wanted to recurse on is the list 1, 2, 3. So first let's look at the contract a little. With all of these x and y, students also tend to get confused. What it really means is just if you say something is value x, it means we don't know what it is. It's kind of like the value type any, but every single occurrence of x has to be of the same type. So in this case, since I have a list of 1, 2, 3, and my contract says this is in fact a list of x, then I know that the value x in this case has to in fact be a natural number. Another one to look at is my second element, which is empty. We know empty is a list, so we can say over here, the value of y for this exact example will be a list. So we can actually go ahead and fill in the rest of it as well. And this does work with cons because cons is in fact something that can intake a natural number, intake a list, and then produce to you a list as well. Any questions about how to distinguish between the types in the contract so far? Okay, if not, then let's move on to see the rest of this example. Like I said, foldr is really just an abstraction on simple recursion. And in this case, since we're recursing through a list, let's look at a template for performing simple recursion on a list. So this is the templates we're usually used to. We know that a list has two cases. It can either be empty or it can be a recursive definition of cons, any, and then another list on top of that. So we have our usual two cases. We have what happens if the list is empty as our base case, and also if it's not empty and in fact it's another list in our recursive case, then like I always say, we need to do something with the first and then simply recurse on the rest. We don't have to worry about the recursion, it'll take care of itself. So if you look at the space for the dots, there's really two things that we need to fill in. One is what gets produced in the empty case, and the other is in our recursive case, given our first element, and then given the results of our function, how do we put the two of them together? What function do we use to put the two of them together? Well, starting off with the empty base case, if the list is empty, we usually like to say that in this case, our answer produces empty. And in the else case, if we're given the first of the list, which is a natural number, and we're given the results of the function f, which in this case we know to be another list of numbers, then to put the two of them together, the function we really want to use is cons. So hopefully this actually looks familiar to you guys because the fact is we just filled in empty for the base case, cons for the recursive case, and that's exactly what we had before in our foldr. So the idea with foldr is the first function you give it should really be the function it uses to join together the current element you're looking at, which in this case is the first of your list, and the recursive results you expect to get from the function itself. In this case, it's just another list. So cons is going to be used to put the two together. And our second parameter over here is really just the base case for our simple recursion. So in this case, our base case is empty. So any questions about, and using this, the result we're going to produce is just list 1, 2, 3 in that order. Any questions so far about how full-dar works or build list works? Okay, if not, then let's move on to our last abstract list function, which is fold out. So fold out and fold are very, very similar, except in one way, which is the idea that fold R is an abstraction on simple recursion, meaning anything you can do with simple recursion, you can do using fold R. And fold out, on the other hand, is an abstraction using accumulative recursion. So anything you can do with accumulative recursion, you can then translate directly into fold L. So once again, let's look at an example of this. We have fold L, cons, empty, and the list that we're working with, which is just list 1, 2, 3. So like before, we can go ahead and label all of our types. We know that our list is a list of X, and since in this case, everything in my list is a nat, we can conclude that X in this case is a nat. So if X is a nat, then the function we need, and we're also working with empty, which is a list, then the function I need to combine a nat and a list together can be cons. And in this case, when a cons takes a nat and a list together, it produces another list of y, another list, which is the value of y. So using this example, let's see how it looks in a cumulative recursion. If we're doing a cumulative recursion on a list, which is hopefully something we're all quite used to, we can once again look at the template over here. We know that when we accumulate on a list, the empty case, so our base case, will always produce our accumulator. We always want to simply give back the accumulative answer we have made up until this point. And then in our else case, if we haven't reached an empty list yet, then we know we want to call our function and accumulate the accumulator that we've been collecting up until now by somehow joining the first of the list, so the current element we're looking at, with the accumulated answer so far. And to do this, we need a function, and of course, we also recurse on the rest of the list. Another thing to remember is that usually, not necessarily, when we do accumulation, we tend to need a wrapper function because it's very unlikely that the end user asks us to make them a function, which includes having them give us the initial accumulative value. So that's why I also included the wrapper in here. So as usual, all the wrapper has to do is give our accumulative function the list, but also decide on what is the initial value of the accumulator that we have. So once again, we have two ... we have two values in the fold R, and luckily they match. Well, not luckily, they match. So usually when we're dealing with a list, we always start our accumulator with empty. So that's also to say, if in our base case, the first thing we get is an empty list, then we want to produce the correct accumulator, which is in this case, empty. Otherwise, in our function over here in the recursive call, if we have to join together the first of our list, which we know is a nat, and the accumulated answer so far, which we know is a list, then to do so, we can use the function cons. Once again, these two simply match back to the parameters that fold L takes. The first one being the function used in the recursive case to join answers together, and the second one being the initial value of the accumulator for our cumulative recursion. So this would produce as a list 3, 2, 1 in that order. So if you ever have trouble remembering this, a good way to look at it is fold R produced us the final list 1, 2, 3, which is a match for a given list 1, 2, 3. So the idea is kind of like you folded in the right direction. So you started from the left and then you were given the numbers 1 and then 2 and then 3. Whereas fold L, you start it from the right, fold it to the left. So if you read the list that way, then you end up with the answer 3, 2, and 1. So that's not exactly how the inner workings are. This example over here with the template is a better demonstration of that. But in case you need kind of a quick fix to say which one was filled out and which one was fold R, this is a quick and dirty method for that. Fold R means you're folding to the right direction. Fold L means you're folding to the left. Any questions about any of the 5 abstract list functions we've presented up until now? Awkward silence is a lot more awkward when there aren't actually students sitting in front of you. Okay, if there aren't any questions, or if not yet, because you can always play this back and ask it later, let's move on to actually warming up with abstract list functions. So the brilliant ISA who wrote this decided we should do something like an abstract list function matchmaker, which I thought was absolutely adorable. So the idea is each of the below mini programs can be solved with a single abstract list function call. And as a reminder, some abstract list function calls we've just seen include fold R, fold L, build list, map, and filter. So the idea of this question is to match each of the problems, is to match each of these to a problem it would be most useful for amongst our choices for. So that means given A, B, C, D, E, what's the best abstract list function to use to go ahead and solve it? So let's start with A. Given a list of file names, we want to add the string temp to the start of each of the file names. What would be the best abstract list function to use? ISAs, if you're in the chat, please feel free to answer. Okay, well, in this case, the idea is the list that we're given needs to be the same length as the list that's being produced at the end, right? If we just want to add the string temp to the front of each of our file names, we don't want to start accidentally losing file names in the middle. So the best abstract list function to use in this case would be map, because fold R and fold L tends to just produce an element at the end. It's not necessarily a list. Build list starts off by taking a natural number. In this case, not it does produce a list, but in this case, we're also intaking a list. And then last but not least, we have to choose between filter and map. And the reason we choose map is because we don't want our list to accidentally get shorter. So the next question would be, if we wanted to just produce a list of numbers counting up to the days that Shawarma Plus will reopen, what function should we use? How about Jimmy Pam, who is the favorite TA of Boasted Trees? What abstract list function should we use? Okay, Jimmy might have left the conversation. So in this case, if we wanted to count up to the number of days until Shawarma Plus would reopen, the best thing we can do is use a list, build list. This is because we're given a natural number to start with, and the only abstract list function that processes that is build list. So the next one would be if we wanted to reverse a list of file names, what function should we use? So in this case, it kind of sounds like something we would either need simple recursion or cumulative recursion to accomplish, because we already have the list we want to reverse. We're not trying to build one up. We aren't really changing every element of a list in a specific way. That would be map. We're not trying to make the list shorter. All we're trying to do is flip the order. So filter is out as well. But yeah, definitely we can use fold L or fold R to do this. So in this case, either one would work. And then another question would be, given a list of word trees, produce all the word tree that are just strings. So given a list of word tree, produce all the word tree that are just strings. Okay, so for this sounds like kind of a filter question because we're restricting what we want in the list. In this case, we had some sort of list, but all the ones we want to keep are just the ones that are strings. So in this case, we should use our filter. And it's completely fine for this list to get shorter. All right, the last one will be given a grocery list of symbols, determine if toilet paper occurs more than 3 times in the list. Hopefully, that's none of you. Please be respectful and don't buy out all of the toilet paper, just get what you need. But in this case, to count if something occurs more than 3 times in a list, once again, this isn't really making the list shorter. This really isn't editing every single one of the elements to do something. This really isn't filtering out just a single type. We're not saying filter it out if it is toilet paper. We're trying to say how many occurrences of there are there of toilet paper. So the only ones we're left with is fold-R or fold-L. So either simple recursion or cumulative recursion will be able to solve this problem. Okay, are there any questions about ALF matchmakers? Okay, if not, then I'm gonna move on and let's actually look at writing a couple of abstract list functions to do the task. So earlier we were able to identify which abstract list functions to use. Now let's actually write the abstract list functions we need. So to start off, let's say I wanted to sum all the numbers in a list. So sum list 1, 2, 3, 4, 5, 6, so that it produces 21. I would want to use something like fold-R. Because once again, if we look at the contracts, so if you're ever confused about which abstract list function to use, a really good idea would just to be looking at the contracts of all of them. So if you look at the contracts, the only 2 functions that produce a single value that's not in list form as its result is fold-R and fold-L. So in this case, since my final result is 21, which is not a list, I know I'm limited to using either just fold-R or fold-L. So in this case, it doesn't really matter. To me, I decided to go with a simple recursion solution in this one. So I decided to use fold-R. And all I have to do is fill in what I need as a function in my recursive case and what I should do when I hit the base case. So if I wanted to sum a list from 1 through 6, then in my base case would be if I were given an empty list. So what's the sum of a list that's empty? 0. So in this case, my base case would just be 0. And then my recursive case, so given the first of my list, let's say 1, and then given the result of my recursive function, which is the sum of the rest of my list, what function do I need so that I can combine these 2 answers and then get the sum of my entire list? So because it seems like there's a lot of lag, I won't really be able to get too many. Oh, there we go. Plus, perfect. Thank you so much for answering. So in this case, if I have the first value of my list and I have the sum of the rest of my list to get the sum of my entire list, I just use plus. So I filled in my abstract list function, and this is the one-liner solution to solve this problem. So I circled it in green, but I forgot to mention it. And the whole idea is with a lot of these questions, you are not allowed to use explicit recursion. And you might think this kind of is limiting for this tutorial, but it's also what you're expected for this week's assignment. So make sure you practice that as well. So the next question we can look at is double. If I want to double each number in a list, what abstract list function should I use? Well, to start off, we can say this function intakes a list and produces a list. So very likely, I'm going to use either map or filter. Now, the list that I'm given is the exact same length as the list that I produce. So very likely, it'll be map instead of filter because filter, once again, always leaves us a chance of the list getting shorter. So in this case, I want to use map. Thank you for saying map in the comments. And all I need to do is give map a function to do what I wanted to now. Yes, exactly. So there really isn't a built-in function called double the same way there is like +1. So if we wanted to do something special like this, what we can instead do is write our own. So if we intake a value and we want to produce it multiplied by 2, what we can do instead is use lambda, which is what we just reviewed earlier in this tutorial. So lambda, once again, is a nameless function. If we want to call lambda, all we have to do is put the entire lambda definition right in the spot where we would normally put our function name. And in this case, lambda is just going to take in one element at a time from our list. So we're going to give it the first of the list, and then the next, and then the next, and then the next. And then what it's going to produce is just that element multiplied by 2. So perfect. The answer in the comments is correct. And that is how we write double list. Okay, 2 more of these. I swear we'll get through them. I guess the good thing is I tend to go overtime on my tutorials anyways, and that's usually a problem because I get kicked out of the classroom or I get in the way of the next class that's trying to happen. Nice thing is with a stream, no one can really kick me off, so it's completely fine if I go over. And if you tune out by then, that's completely fine as well because you can always come back and watch the recorded version. Yes, I'm recording. Okay. So the next function we're going to try to do is keep all the numbers in a list that are divisible by 3. So we call this a keep triple, and you are given a list. So once again, if we just go through the contracts of all of the abstract list functions we have, we'll know that we're choosing between either filter or map because we are only given one list to work with. So given this list to work with, we can also see that the list produced is in fact shorter than the list that we're given, which means it's going to be filter because map always produces the list of the same length. So in this case, we know the function we're using is filter, and the only question we have to give now is what's the predicate function that filter is going to use? What kind of predicate function exists that can say whether or not something is divisible by 3? So thank you in the comments once again. Unfortunately, there isn't really a built-in function that checks if something is divisible by 3, but it is a nice short function we can quickly write for ourselves, once again using lambda, which is what we just learned. So instead, I can just put the entire lambda definition in the spot where I would normally just put a function name such as add1, 0, symbol. In this case, I wrote that lambda will intake one element, so that's the element of the list one at a time, and then produce whether or not the element, when divided by 3, has a remainder of 0. If it does, then we know it's divisible by 3. It will produce true, and filter will keep it in the list. Otherwise, it will produce false, and filter will leave it out. Okay. And the last question is to create a list with odd numbers from 1 through n. So odd list, you're given just a natural number. In the comments, someone gave an answer in Python instead of bracket. That's totally fine. So in this case, the question is given a natural number, meaning there's only one abstract list function we can possibly use, and that's build list, because build list is the only abstract list function out of the 5 that we give you that intakes just a natural number and produces a list. So in this case, we're going to use build list. We're just going to build a list from 1 through n first, which is the initial question. But then from here, we just have a list from 1 through n. What are we going to do with that? In this case, since the question says we only want to keep the odd numbers, this is becoming more of a filter question again. So all we have to do is produce a list from 1 through n, and then filter out for the values that are odd. So this is kind of 2 for the price of 1 abstract list functions. Okay, any questions about any of the examples that we did? Okay, if not, then let's move on to the next section of the tutorial, which is writing problems. This will be quite interesting because this is normally when I give students some time to come up with the answers by themselves, and then we take it up together. Or if you guys have any questions, this is usually when I walk around and try to help you with that. So since I doubt there's many people right now in the live stream that are getting their rackets out and try to code this up, what I'm just going to do is present the question and then pause. So if you are watching this later, you can pause the video and try to do this question on your own. And then after that, I'm going to explain the solution. So to start off, we have problem 2, which is make posins. And what we want you to do is essentially write a function called make posins, which consumes a list of x values and a list of y values. And then using both lists, which are of equal length, we want you to produce a list of posins, where the ith position consists of the ith x and the ith y. So what that really means is, given a list of x, given a list of y, we want you to make a list of posins with x1, y1, x2, y2, x3, y3, and so on and so forth. So this would be an example of what should be produced. So once again, if you're tuning into the live stream, please go ahead and try this now. If you have any questions, please use the stream chat where our ISAs are all standing by and waiting to answer your questions. Yes, a posin is a make posin num num. That's definitely something good to know. If you're writing bracket code, I don't think there should ever be a return value in there because it's functional programming. There also shouldn't be any loops. We only use recursion here. And in fact, no explicit recursion for this question. We only use abstract list functions here. So I'll give you guys maybe a minute. I'll drink some coffee and then we'll take up these solutions together. I didn't get a chance to eat lunch. Okay. So I know that wasn't a lot of time. If you're still doing the problem, please feel free to pause it and tune back in. Even though it is a live stream, you're always allowed to take your time with the problem. So I guess that's one benefit of having it online instead of in person. If not, then let's take up the solution together. So the first thing to note is what kind of abstract list function should we use for the given problem? Well, we're given lists and we want a list of the exact same length at the end. So this kind of sounds like a map problem, except for the fact that by our contract, map only really takes in one list at a time. So the really important thing to note here is using fold_r and fold_l, just those two abstract list functions, you can actually write all of the other ones that are built into Racket. All of the other abstract list functions in Racket are actually just written using fold_r and fold_l. Because if you want to use map, but kind of a little different from the one that's given to you, you can always rewrite your own version using fold_r or fold_l. So this is also a really good reason of why I showed you an in-depth analysis of how map really works versus how fold_r and fold_l really works. If the question ever comes up to write your own map, you should be able to do it using the examples I gave earlier. So let's actually just do that. In this case, what we can do is we can write map and it's given, oh, never mind. So the solution that is given, I thought it gave you a different one first, just to kind of hype it up a little, but the solutions we give actually takes two lists, even though we're using map. So I wanted you guys to kind of like write your own map earlier, kind of as a practice, and then tell you that in fact Racket does, in Racket map does take in as many lists as you want, and it just concurrently goes through each item in all of the lists that you give it. So each item in lockstep, and then feeds it to the function that you give it. So in this case, you're given two lists of equal length. Map will in lockstep give you the first element of the first list and the first element of the second list to process. So in this case, we can write our own function, which is lambda. It takes in two parameters, which is x and y, x being the first value of the list 1, and y being the first value of list 2. And then from here, all we have to do is feed x and y into makeposin to get a list of posins at the end. Any questions about this? I thought we had set you guys up for a different question. I misread the slides. That's okay. But if you do want some extra practice, writing map using fold-R and fold-L is a great way to practice. You can also write all of the other abstract list functions by yourself as well. I think that's pretty good. Especially if you're stuck at home with nothing else to do. It's a great chance to get some extra practice in. And if there are no questions, then the last thing I want to say is that we didn't actually have to write lambda because makeposin is already a function which takes in two values and then produces just a posin. So in this case, we didn't have to write lambda as a buffer to say, we'll intake the x, we'll intake the y, and then feed it to the makeposin function. Instead, all we have to do is feed map the makeposin function, and that could be done a lot easier. Any questions so far? Okay, if not, then I am almost out of time, but that's okay because I'm almost out of questions to do as well. So let's move on to our last problem of the tutorial, which is problem 3, and we've named it multi-odds 2. So this is just a combination of what we want your function to do. So essentially, we want you to write a function called multi-odds 2, which will consume a natural number and produce the product of all the positive odd numbers that are less than or equal to n. So this is the multi, this is the odd, and this is the 2. Great naming, guys. So please go ahead and try this out. So for example, if I gave you multi-odds 2 with the natural number 5, you should produce to me the answer 15 because 15 is the product, the multiplication of all the positive odd numbers that are less than or equal to 5. So I'll give you a minute or two to try this out. If you have solutions or even if it's in a different language, please go ahead and post it in the comments. Okay, so once again, I'm going to move on and explain the answer now, mostly because sitting here in silence by myself is a lot worse than just sitting in front of students in silence. If you are still working on the problem, please feel free to pause the stream. If you are watching this at a later time, please also feel free to pause now and resume when you're ready to hear the answer. Otherwise, the solution we're going to use is essentially a combination of fold-R, filter, and build list. So that kind of also goes into the way we name the problem, which is multi-odds 2. So how do we come to this? It starts off with the idea that you're given a natural number. So out of all of our abstract list functions, the only one that takes in just one natural number and then produces a list out of it is build list. So we know we're going to have to use build list in there somewhere. So we're going to take build list, we're going to take the value we have, which is n, and then we're going to produce that list. The reason we use add 1 is because we're computer scientists and build list starts at index 0. But in math, when we're dealing with natural numbers and multiplication, we don't want to multiply 0 into that. We want to multiply starting at 1 and also inclusive of 15. So in this case, we want to use build list, and add 1. So we get the list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 instead of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and yes, anyway, 0 is not odd, so it would have gotten filtered out in the next step. That is true. That's fine. Good catch. Comments. Okay, so after we have our list of 1 through 15, the next thing we need to note in the question is how we only want to multiply the ones that are odd. So, given a list and given a stronger constraint on it, the abstract list function we're going to want to use is filter, because in this case, as before, it's completely fine for our list to get shorter. So we're going to filter out. The predicate we're going to use is the built-in predicate odd for all of the numbers between 1 and 15 that are odd. So now we're just left with, I don't think I can do this very fast, 1, 3, 5, 7, 9, 11, 13, 15. Okay. And then last but not least, we can't just produce a list. We actually want to multiply all of these guys together. So if you look at our abstract list functions, our options are really just between fold_r or fold_out, because those are the only two functions which intakes a list and then produces a single value at the end, which in this case for us is a natural number. So to do that, in this case, our solution uses fold_r, which is once again just an abstraction of simple recursion. In simple recursion, if we wanted to multiply together all the values of a list, then we have to take care of two cases. One is what to produce in the base case, so what to produce if we're given an empty list. And the second one is given the first value of a list, so given a natural number, and then given the results of recursing on the rest of our list, so in this case, given another natural number, what function can we use to join the two of them together so that we can get presented with the product of the entire list? So in this case, if we have the first value and we have the product of the rest of our list, then to get the product of our entire list, we simply use the function multiply. And then otherwise, for our base case, if we have an empty list, then we know that the product of this empty list is just 1. So that's how we fill in our fold_r. As you can see, we have the function multiply here. We have our base case 1. And then the list that it is working with is just the results of a filter on a build. So this was a really nice, tricky question. It had a lot of components to it, but because once again, we're working with abstract list functions, it's really nice and short. So does anyone have any questions about this last solution here? Okay, if not, then this is actually the end of our stream because I am once again already over time, but I'll just chop that up to I had some technical difficulties throughout the stream. We do provide you with a couple extra questions that you can try on your own time, like this map list of functions and also a stepping lambda problem. So there's two of these, one with just regular lambda, one with nested lambdas. I showed you guys a stepper question for lambdas earlier when I was talking about it, but if you want to get more practice and just get really, really comfortable and good with it, these are definitely the ones to go to. If you guys have any questions, please message us on Piazza and we will be happy to help you there. Otherwise, Roger, your ISA, also has regular office hours, which are online as well. Please go ahead and attend those. And if you need help because there's too many students, I'm sure the rest of us will like to join in as well. Otherwise, thank you to like the 11, 18 people who tuned in to this tutorial, or the 7 people that are still here. I would say that's probably equivalent of a class size we can expect on a 8:30 Monday morning or Friday morning kind of tutorial in winter. So for the fact that you're right now in the middle of a pandemic, that's not bad. I think that's probably Roger, but someone in the comments would like to say, please see Piazza post 558 for the office hour times. Before we leave, are there any other questions? Would anyone like to see my dog? Okay. So, treat for the 6 people who are still here. Normally, my tutorial students get to see my background, which is this dog, but you guys on the live stream get to see him now. Sorry, I woke him up from a nap. All right, bye.